A presentation on the Karatsuba algorithm, an advanced method for fast multiplication of large numbers using the divide and conquer approach. Developed by Anatoly Alexeyevich Karatsuba in 1960, this algorithm significantly reduces multiplication time compared to traditional methods. Today we'll explore its mathematical foundations, implementation, advantages, and real-world applications, providing a comprehensive understanding of this powerful computational technique. Welcome you all. I am Bharath M, of fourth semester CSE Artificial Intelligence Department and at the Sri Venkateswara College of Engineering, Bangalore. The subject I am going to be presenting here is analysis and design of algorithms, and the topic is the Karatsuba algorithm for fast multiplication by divide and conquer. This one, let us look on an introduction to multiplication algorithms. Traditional multiplication algorithms such as the grade school method have been foundational in arithmetic. These methods involve multiplying digits individually and summing partial products resulting in an order of n square time complexity. While, while simple, they become inefficient for large numbers. With the growing need for faster computations in cryptography and numerical analysis, advanced algorithms like Karatsubas have emerged, leveraging divide and conquer strategies to enhance performance and reduce computational complexity. What is the historical background of the Karatsuba algorithm? The Karatsuba algorithm was discovered in the 1960s by Soviet Union's mathematician Anatoly Alexeyevich Karatsuba. At the time, the standard multiplication method was inefficient for large numbers. Karatsuba's insight was to use a divide and conquer strategy to break down the multiplication process, leading to a faster, more efficient algorithm with a time complexity of order of n to the power log 3, approximately order of n to the power 1.585, which marked a significant advancement in computational mathematics. This is about the history and the historical background of the Karatsuba algorithm. Moving on to understand divide and conquer approach. What is this divide and conquer approach which we are going to be seeing here? The divide and conquer approach is a fundamental algorithm paradigm used to solve complex problems by breaking them down to simpler subproblems. It involves three main steps: dividing the original problem into smaller, manageable parts, conquering by solving each subproblem recursively, and combining the solutions to solve the original problem. This technique improves efficiency and reduces computation time, making it ideal for algorithms like Karatsuba's for fast multiplication. Mathematical foundations of Karatsuba algorithm relies on polynomial representation for multiplication. It breaks down to large numbers triple x and triple y into smaller parts, which is a variable. Specifically, by multiplying these smaller parts and using relationships, the algorithm achieves faster multiplication. Next, the basic idea of Karatsuba algorithm: simplification and multiplication by breaking down the problem into smaller parts. For two numbers, variable xxx and yyyy, it splits each into high and low halves. It then computes three key products, and by combining these, it reduces the multiplication complexity to approximately order of n 1.585, order of n to the power 1.585, order of n 1.585. Step-by-step explanation of Karatsuba algorithm, how this exactly happens, let us see. First thing, split the numbers. Divide the input numbers triple x and triple y into high and low parts. Compute products, that is calculate three products. Combine results, use the formula. And a recursive application, apply the algorithm recursively to further break down and solve smaller multiplications. These are the step-by-step explanation of the Karatsuba algorithm. Next, comparison with classical multiplication algorithm. The classical grade school multiplication algorithm operates with a time complexity of O n order of n square, where n is the number of digits. This method multiplies each digit of one number by each digit of the other, making it inefficient for large numbers. In contrast, the Karatsuba algorithm uses a divide and conquer approach to reduce the number of multiplications, achieving a time complexity of order of n to the power 1.585, which is order of n log 3, sorry, n power log 3. This results in significantly faster computations, especially for large inputs. This is the comparison with classical multiplication algorithm. Next one is on the time complexity analysis. Karatsuba algorithm reduces the time complexity of multiplication from order of n square to order of n log 3 to the base 2, which is approximately um, order of n to the power 1.585. Smaller multiplications, this is achieved by dividing the problem into three smaller multiplications and combining their results. Each recursive call involves splitting the numbers and performing a constant number of additional operations, leading to a reduction in the number of multiplicative operations compared to traditional methods. This makes Karatsuba efficient for large number multiplications. Space complexity analysis. The space complexity of Karatsuba algorithm primarily depends on the depth of recursion and the space required for intermediate results. In general, the space complexity is order of n, where n is the number of digits in the input number. Each recursive call requires additional stack space, and intermediate storage for results is proportional to the size of the numbers. The space usage for recursive call is logarithmic in relation to the number of digits due to the divide and conquer approach, making Karatsuba relatively space efficient. This is about the space complexity analysis. Advantages of using Karatsuba algorithm: faster multiplication, as we saw, reduces time complexity from order of n square to order of n 1.585 to the power, making it significantly faster for large numbers. Efficient for large numbers, particularly beneficial in applications involving large integers such as cryptography. Reduced multiplications minimizes the number of required multiplications compared to classical methods. Practical implementation is efficient in practice for a wide range of integer sizes with straightforward recursive implementation. Foundation for further algorithm serves as a basis for more advanced multiplication techniques like Cook and Sonnenstrassen. And if there are some advantages, there will be a few disadvantages and limitations and challenges. It is a overhead for small numbers. Algorithms overhead can outweigh its benefits for smaller numbers compared to simpler methods. Fine, I can get that. Recursive depth, deep recursion can lead to high memory usage and stack overflow issues in languages with limited recursion depth. Implementation complexity, more complex to implement than traditional algorithms, requiring careful handling of intermediate results. Numerical stability may encounter issues with numerical stability in floating point arithmetic or very large numbers. Not always the best choice. For certain applications or number sizes, other algorithms like Strassen's or optimized school book of multiplication may be more efficient. These are the 5 limitations and challenges faced by the Karatsuba algorithm. What is the applications of these algorithms? Where are these algorithms used? They are used in cryptography, uh, used in algorithms for encryption and decryption where large integer multiplications are common. Then computer algebra systems facilitates fast polynomial and large number arithmetic in software like Mathematica and Maple. High performance computing employed in numerical simulations and computational mathematics where efficiency is crucial. Big data processing supports efficient multiplication operations in data analysis and large-scale computations. Scientific computations is useful in scenarios involving large numerical calculations such as simulations and modeling. Fine. These are the applications of Karatsuba algorithm. Optimizations and enhancements. Hybrid algorithms combine Karatsuba with other methods like Cook or T-based algorithms to improve performance for specific cases. Implementation tweaks optimize recursion, depth, and handle base cases efficiently to reduce overhead and stack usage. Memory management use iterative approaches or tail recursion to manage stack space better and avoid overflow issues. Parallel processing is leverage multi-threading and or distributed computing to further speed up multiplication by handling different parts of the algorithm concurrently. Cache optimization is enhanced performance by optimizing memory access patterns and minimizing cache misses during recursive calls. Comparative analysis with other fast multiplication algorithms, Strassman's algorithm, Tom Cook algorithm, Sonnage-Strassman's algorithm, FFT-based multiplication, classical algorithms. There are so many other fast multiplication algorithms, and this is a little advantaged compared to those other algorithms. Future directions and research which can be seen: quantum computing, adaptive algorithms, hardware optimization, high dimensional multiplication, parallel distributed computing. In all these places, the Karatsuba algorithm can be used in future. Before we finish, Karatsuba algorithm represents a significant advancement in multiplication techniques, reducing complexity from order of n square to order of n to the power 1.585, which is order of n power log 3. By leveraging the divide and conquer approach, it achieves faster performance for large numbers, making it invaluable in fields like cryptography, scientific computing, and data processing. While it has limitations such as overhead for small numbers and recursion depth issues, its application and potential for further optimization ensure its continued relevance and impact in computational mathematics. This was the conclusion of the Karatsuba algorithm, and see you all very soon in the next video. Thank you very much for being a part of the video. See you soon.